Arkadan geliyor. Geliyor Arkadan.
Hi everyone. First of all, thanks to organizing committee for making this organization exist. Eray is a second year double major student in math and physics at Beacon University, and we have been studying reinforcement learning, neural networks, and their integration. Today, he will present an overview of these topics. Eray, the floor is yours.
Thank you, Hocam. First of all, I want to thank my mentor too, Alaaddin Hoca, for his constant help and effort throughout the summer. And this will be the flow of my presentation. I will be talking mostly about reinforcement learning, and then I will move on with deep Q learning techniques. And if we had time at the end, I want to share you with some implementations. And as an introduction, let me share you with some applications. For instance, Google DeepMind's well-known AlphaZero bot and OpenAI's Dota 2 bot are the two famous examples that use RL methods. And apart from that, goal-based robot arm simulations, traffic light control systems, and trading pods that sells and buys stocks on market can be given as applications where RL can be used. And what is learning, first of all? A learning algorithm is from a data set, takes the information and use it to find the hypothesis among a hypothesis class to optimizes a performance criterion. This performance criterion might be accuracy or something else. And what hypothesis class and hypothesis is will be clear after some examples. And so the trend is learn from data, perform tasks without explicit instructions. But what about reinforcement learning in particular? There are two major components. One side is agent, and the other side is the environment. Agent takes actions, and environment responds to those actions by giving a reward and transitioning the states of agent to another state. And this is the framework. And from a concrete example, like let's take the example of chess. Agent is the player, and environment is the game, and state is a certain position, and action is a valid move. A reward is a function which gives higher scalar amounts to more valuable actions. But how can we formalize all these mathematically? Even though RL can apply to many problems, focus of this presentation is Markow decision processes. And to understand that, we first need to look at Markov chains. And a stochastic process, in Markov chain there are two concepts, a stochastic process and a Markov property. So a stochastic process is a sequence of random variables where the index is usually the type. So it indicates that the process involves some sort of randomness. And Markov property is, in the simplest terms, a process's future being independent of its history. Again, from the example of chess, a certain position evaluation is independent of how we came to that position, and hence that's its history. And even though we afterwards we get that knowledge, that would not change our evaluation about the position. And a Markov chain is a stochastic process describing a sequence of possible events with the Markov property. Here we see an example where agent might be a man, for instance, and states are some events that he can perform, and numbers are the properties, implying that this is a stochastic process. And note that these properties are independent of where we came to that state. For instance, from the example of state TV, the probabilities on the arrows are just independent of how we came to that state. And a Markow decision process is very similar to what Markov chain is, but with addition of action space and a reward function. And it's a tuple of 5 state. There is state space, action space, transition function, which takes state, action, and state triple, and it gives when agent is at state S and takes the action A, it gives the probability that next state being S prime. And reverse function takes a pair, state and action, and it is the expectation value of the reward, and it, by the way, it gives a real number, a scalar amount, and when action takes at state S and takes an action, it is the expected value of the reward. And the expectation calculation is applied because of the transition function, the probabilistic nature. And finally, gamma is the discount factor, and it simply stands there for implying that rewards at the near future worth more than rewards at far future. Okay, these were the environment dynamics, and what about agents? Policy is the function that rules how agents should behave, and it defines how an agent selects actions. And in the stochastic case, it takes a state and action pair, and when at state S, it gives the probability that agent selects the action A. And in that regard, for each state, for each state and action, it kind of gives and provides a probability distribution. And yes, and the trajectory is the kind of a record of the agent's interaction with its environment. And this record consisting of state, action, reward, state, action, reward sequence. And we will use it frequently. The return, which is denoted by G, by the way, is the function that is the discounted sum of rewards, and we multiply the rewards at each time step that we get by the factor of gamma to the power t. So here we immediately understand that gamma needs to be between 0 and 1 to get smaller as the exponential increases. And below, at the figure below, we see a Markow decision process. Transition function is the thing that enables gives the probability between transitioning between states, and transitioning is only possible by taking some actions, and those actions are selected according to some policy. And after these things happens, a reverse function attains this thing to a real number, indicating how valuable it is. A feedback. It is a feedback. So the ultimate goal of reinforcement learning is to find a policy that maximizes the return function. In that regard, the return function is the objective function. But how to find it? How to find it? There are several methods, and all of these methods use two core functions: value function, v-value function, and q function. V-value function is the return if the agent follows policy pi from state S. And it is a measure of how valuable a state is. And so agent is at state S, and afterward it should select all of its actions according to given policy. And well, this value function is the expectation value of the return afterwards. That is the sum of discounted rewards. These are the rewards, and this is the discounted. And return for a discount. and optimal value function is for the v value function that is formed by a policy such that v value function is maximized for every state in state space. And yes, the other function is q value function. This time it measures the quality of a given paper, state and action. And the difference is that the additional condition that agent should also take the action A. And it is again the expectation value of the reward return afterwards. And yes, the optimal Q value function can similarly be found. And the one key difference between V value function and Q value function is that optimal policy can directly be obtained from Q value function by defining it as choose and telling the agent that choose the action that maximizes the, of course, at each state, choose the action that maximizes the Q value function, the optimal Q value function. And this would be our optimal policy. But this does not apply to V value function because you need the additional knowledge of transition function and reward function no matter what. Then the case is V value. Okay, now let's look at an example. Here, there are 7 states and 2 allowed actions, left and right. And let's say we have an agent that can travel around these states. And there are 2 reward functions defined. One is from transitioning from S2 to S1 and other from S5 to S6. And of course, the goal of the RL was maximizing these rewards. And yes, we can, for the simplicity, let's take gamma as 0.5. Now, let's define 2 policies. One policy say, and notice that these are rules for controlling the behavior of the agent. Take the action L, whatever your state is. And the other is, says, we define policy 2 as take the action R, whatever your state is. And let's try to understand what is the value function of state S3 with pi 1. When the necessary calculations are done, it is found to be 6 because when we are at S3, we check the policy. Policy says perform the action left. We go to left, and again, policy says left. We move to left, and we arrive at S1. In that sense, we obtain a reward of plus 20, and then we reach the terminal state with which ends the game. And in total, it is found to be 6. And when we calculate the same value function of the same state, but with different policy, we obtain a different result, which shows that different policies may value each state differently. So in that sense, this for the values of state 3, policy 1 do a better job. And when we try to calculate the Q value function, this time the only thing we do additionally is that taking our first action just by looking at the argument of Q function. And when we are S2, for taking our first action, we check here and not the policy. It says left. We go left and then continue by taking actions what policy says. And since this is pi 1, we again take the action left and the game is terminated. Then we do the calculations. The result is found to be 12. But when we try to evaluate Q value function of the same state, but this time with first taking the action R and continuing with what policy 2 says, the Q value function of the same state and with the same policy now is found to be 3. So again, we see that when we are at state 2, starting with action left is more logical. These are the Bellman equations, and they are frequently used in the methods, the RL methods. and they bind value functions of one state to value functions of the next state in a recursive manner. Here, the policy gives the probability of selecting action when agent is at state S, and similarly, transition function gives the probability of transitioning to state S prime. And when we multiply this expression by these terms and sum over the action space and space, it is actually a simple expectation calculation. And this term is actually the recursive form of the return by just writing the immediate reward and expressing the rest of the rewards in terms of a value function, and by, of course, multiplying it. Similar logic also works for Q function, but I will just skipping it for the time being. And there is Bellman's optimality equation, which is a recurrent expression for optimal V. And the only difference between ordinary Bellman equation is that this time we select we calculate just for the A that maximizes the rest of the expression. And all of these equations will be used in RL methods, as we will see soon. Okay, this is the first method. I will just briefly go and just explain what it aims and how it does it, but not go into details. So the question is, we are given a policy and we want to find the value functions of corresponding to that policy. But how can we do that? By starting random values for value function. We start with random values and we update them according to Bellman equation. Just yes, and this converges our estimates to V of pi, and from V of pi we can also find estimate for Q of pi. And how to improve the given policy? By a greedy approach, we can construct a new policy, and by the policy improvement theorem, it's guaranteed to be better than our initial policy. So this was policy evaluation, and this is policy improvement. And the repeated application of policy evaluation and policy improvement is called policy iteration. And the end result of this policy iteration algorithm is guaranteed to be to give the optimal policy, because the result is guaranteed to satisfy the optimality equation. But when we apply the update according to not this time Bellman equation, but Bellman optimality equation only, this time this estimates for V does not converge to V of pi, but our optimal V functions. And the convergence is actually a relatively simple group. We first observe that this update can be written in form of an operator, and then Bellman operator is a contraction mapping is a theorem, which has a nice proof. And from Banach fixed point theorem, it assures that it is for just contraction mappings, but since Bellman operator is also a contraction mapping, it works also for Bellman operator, which is the update, which is simply this update to vector form. And it assures existence and uniqueness of a fixed point, which is which can be demonstrated to be the optimal value function. Other method is Monte Carlo methods. Here we use computer simulations and randomness to solve problems that are deterministic in principle. But I mean, something is sampled, and what in Eray methods, what is sampled is trajectories, the recording of agents' interactions, state action reward sequence. And from that sequence and these samples, how can we construct an estimator for V value function, starting from S? And of course, we want to estimate V value function for a particular state. And we can compute, this is G return, by the way, compute return from the first recurrence of S. This is simply adding up the rewards by first discounting them with the factor of gamma. and then store these values and take the average. And this would give an unbiased estimate. But now, what we have done, we estimate the v-value function with given policy pi. Now we want to improve the given policy. And for that, we apply very similar thing, but this time to Q function. And for each, and after this application, for each episode, we update our policy from the estimated Q function by just saying that to agent, when you are at state S, select the action such that it maximizes the your current estimation for Q. And again, this converts to the optimum policy. And another method is Q-learning. Here, we don't know transition function and reward function. But from the Bellman's optimality equation is converted to an update rule. Here, we work from Q-value function. This is our estimate. Again, this is the update term. This is learning rate, and this here, this is the target, and we get this scalar amount of reward from the those simulations, and this part is just our previous estimate for next step by taking the action such that maximizes the Q function, and this is our again the current Q. Okay. In a nutshell, I will go on. Just I will finish in a couple of minutes. This method requires storing Q values for each pairs of state and action in a table. But when the problem is unmanageable and its state space is too large, this doesn't work, and deep learning techniques are required. By using neural networks and backpropagation algorithm, we construct a deep neural network in such that its input is states and output is Q-value functions by with each of actions. Yes, and this is called deep Q network, and the whole thing is called deep Q learning. This arises some problems with stability. And solution to that is found to be an experience replay by simply sampling not from just interactions, but constructing a replay buffer that stores the last n examples and then sampling from there, and constructing another network for targets and updating it more infrequently. And those functions here. Okay, an implementation is in Atari games. I could not watch it at the moment due to time restrictions. And another, and the more actually interesting one came from drone racing. It is a very recent work, and AI here, the AI drone, actually we see that AI drone wins the race over many times against the professional and world champion humans. And these are my references. Thank you.
Thank you. Is there any question?
Great presentation, by the way. I want to